Assalamu alaikum and hello everyone. In this new series of videos, we are going to solve the exercises from the chapter 1 tutorial sheet together. We are starting with this first video where we will learn how to rigorously verify if a set of vectors is a vector subspace. This is an absolutely fundamental skill in linear algebra. Before we dive into the first example, let's quickly recall the rules. To prove that a subset F is a vector subspace, we need to verify three conditions. The first one is the non-emptiness. To do this, generally we verify that the zero vector is in our set. The second condition is the closure under addition. To do this, we take two vectors in our set and we have to prove that the sum of these two vectors are also in our set. The third condition is the closure under the scalar multiplication. To prove this, we take a vector in our set, a scalar, generally a real number, and we have to prove that the product C times U is also in our set F. So let's start by applying this to our first set, F2. Let's check the properties step by step. For the non-emptiness, we can see that 0 plus 0 plus 2 times 0 equals to 0. Then the zero vector of R3 is in our set. Then F2 is non-empty. The second condition, let's take two vectors U and V. If we add their equations, x1 plus y1 plus 2z1, and the same equation with the second vector, if we sum this, we get x1 plus x2 plus y1 plus y2 plus 2z1 plus z2. Then the sum of our vectors u and v are in our set F2. For the third condition is the closure under the scalar multiplication. If I have a vector u in our set F2 and I multiply the equation by a scalar C, I get this, which means that C times U is also in our set. Since all three conditions are met, F2 is a vector subspace. If you look closely at the equation of F2, you will notice it is a homogeneous linear equation, meaning it is equal to 0. This is a great news because this exact same logic applies directly to the set f4, f6, and f7. Whether it is a single line or the intersection of two planes, like in f7, all these sets contain the zero vector and are closed under linear combination. I have to remember you this. The two conditions 2 and 3 can be replaced by only one condition, which is proving that a linear combination of two vectors from f2 is also in our set f2. Therefore, they are all vector subspaces. However, be careful, not all equations define subsets. Let's look at the sets f3 and f11. Your first reflex should always be to test the zero vector. If we set x and y and z equals 0, we get 0 equals 1, which is impossible. The exact same issue happens with the set f11, which is a sphere. Again, the zero vector is not in f11, and the zero vector is not in f3. By this, we can conclude that these sets are not subspaces. To clarify this, I know that these sets are not empty because, for example, I have the vector 1, 0, 0 satisfy the equation, then this vector is in f3, but the condition of closure under multiplication by a scalar is not satisfied. To prove this, let's take any vector satisfying this equation. If we multiply this vector by 0, I get this, which is not equals to 1. Then, for any vector u, the scalar multiplication by 0 is not in our set f3. Sometimes the zero vector is present, but the set hides other traps. Let's see this. Let's see what happens when we introduce a product with f5. The zero vector is here because 0 times 0 equals 0. But is it closed under addition? Let's take two valid vectors, for example, 1, 0 and 0, 1. The two vectors satisfy the equation, but if we add them, we get 1, the vector 1, 1. But for this new vector, 1 times 1 is not equal to 0. Then the sum is not in f5, then f5 is not closed under addition. We have similar example like f9. If we take the vectors 1, minus 1 and -1, -1, which both belong to F9. Their sum gives a new vector 0 and -2, but 0 squared plus -2 is not equal to 0, then the sum of the vectors are not in F9. Finally, be aware of inequalities. What about our last set, F13? Here, scalar multiplication is the problem. If I take the vector 1, 0, 0 and multiply it by a negative real number like -2, this new vector violates the condition that the first component must be positive. Therefore, this is not a vector subspace. To summarize, a vector subspace is defined by homogeneous linear equations. If you see non-zero constants, products, squares, or inequalities, it is an immediate sign that it is not a subspace. So practice, and we will meet again very soon in the next video for the rest of the exercises. And bye.